I'd like to invite our next panel to come up to the stage here. And this is going to be on the non-pipeline industry regulatory risk requirements and approaches. So we're going to try to listen to some ideas and hopefully get some lessons learned from other industries, how other regulators are approaching risk. Our first speaker is Bob Youngblood. He is Senior Risk Consultant, Risk Assessment and Management Services at Idaho National Laboratory.
Good afternoon. I'm Bob Youngblood here today with Marty Sadison. This is a clip from the abstract, actually will be, and the talk is reasonably faithful to it. We'll say some generalities and then make a few points about how certain other agencies do this. Department of Energy, NASA, process plants, and the Nuclear Regulatory Commission, in the hope that this helps in some way. And then unfortunately, or fortunately, maybe a lot of what I'm going to say was said already in the morning, but of course I didn't know that when I prepared these. But you can't make sense of the subject without thinking first about the decisions that you're going to make. So the points on this slide are actually from a typical decision analysis text. But when you're doing risk analysis, you're doing it for a decision analysis reason. So of course they apply. The first one listed being high stakes. That sort of sets the scale of your investment of what it's going to be worth to you to do analysis, and then the rest you can see there. Uncertainty was brought up this morning. It's pretty important, and I'll return to that, of course. So to begin with, when the NRC sponsored the first large-scale PRA, the question they were answering was, how safe is nuclear power? But quickly, after that study was done, the emphasis began to be, why is it safe? What is it that makes it safe? Under what conditions is it safe? What should we be focusing on? So the numbers never really go away, but this sort of kind of prioritization 101 is a key application of the method for us. The analysis that answers the questions is a roadmap to what has to be achieved. And actually that was true before PRA, when NRC, Nuclear Regulatory Commission, regulated things based on classical accident analysis before PRA. The point of it was to tell you what to focus on. I'll be returning later to the aggregate risk matter. This is a slide that's actually came out of NRC regulation of byproduct material safety. The point of it is on the left you can see a scale of possible consequences, which in the case of byproduct material ranges at the high end from hazards associated with a food irradiator, which can be lethal. And on the right, what sort of assurance of barrier performance you'd need, both, first of all, to make sure that it actually works, and second, to tell licensees and regulators what sort of analysis is appropriate. So at the high end, you need high assurance, and at the low end, you can afford to be a little more relaxed, maybe performance-based. This slide is about what we would call a graded approach to analysis. And actually, it was covered this morning, too, implicitly. On the left, you start with a decision that you need to make. In the middle, you're choosing the techniques that you apply, qualitative, quantitative. On the right, you have some sort of answer, but the question you have then is this answer good enough? And someone actually said this morning, if you're analyzing alternatives and you're they're not clearly distinguished by the analysis that you did, then you need to work harder. Maybe you need to do a better analysis. Maybe you need to reduce uncertainty in your data. And actually, interestingly, in the late morning, people even brought up value of information. So this slide sort of notionally plots a few tools and methods. The horizontal axis is methods that are more scenario-based or to the right, methods that are more quantitative on the vertical axis. And of course, there are many. You could blacken the slide with tools and methods, maybe subjectively characterized. The origin is not zero. Even prescriptive codes and standards have some notion, usually, of what scenarios might happen and what the consequences might be. At the high end on the upper right, I've put PRA in two boxes. One is classical fault tree event tree, and on the far upper right, simulation-based PRA, which many of us think is getting to be more important, well, certainly more feasible, and arguably, in some cases, more valuable. And in the middle are the sort of hazard assessment techniques that some people would then put straight into one of these index-based, as people were calling it this morning, methods. Now, here's a sort of a notional diagram. Well, not notional. It's a small example of a PRA. It happens to be from a NASA document. It's a piece of a spacecraft system. The initiating event is a hydrazine leak. And then the question is, do you detect that leak? Do you isolate it? If you don't detect it and isolate it, or maybe even if you do but not in time, hydrazine can chew up the wiring and cause you both loss of mission or potentially loss of the craft. And by the way, this is, I'll be talking about NASA, NRC, and DOE. In NASA, of course, you don't have the luxury of shutting off your space flight once it's started. So their models typically look both at loss of mission and maybe loss of crew. They have different figures of merit. NRC, of course, many of their risk models are hardwired to take credit for the possibility of shutdown. Not that shutdown is perfectly safe, but it structures their model. The full power models basically don't reflect the possibility that you'll operate in a bad configuration for a long time. You're not supposed to do that. I think the pipeline industry is not so much like the NRC in that regard. And then I'm not sure, I've seen fault trees here earlier today, but I don't think this is probably not the right time to cover fault tree analysis. But models like this are about as scenario-based as they can be, and they're a basis for quantification of a sort. And clearly, if the ingredients are present, you can use models like this to decide what to focus on. So here's how NASA thinks about that. This is a table from a different NRC document. Table on the left is characterizing the project that you're analyzing. And the table on the right tells you what you have to do. And you can see on there that if public safety is a factor, or if it's human space flight, or if it's just really high stakes, you have to do PRA, by which they mean the kind of fault tree event tree thing I showed you a moment ago. At the Nuclear Regulatory Commission, of course, initially and still even today, they license based on classical safety analysis, where they tell you what challenges to analyze, and you have to show that you can meet those challenges. But PRA has been increasingly a factor in their decision-making. Not so much licensing, but decision-making about whether to intervene in licensee management. So after WASH 1400, the mid-70s, they did change some rules. And nowadays, to get design certification, you need to supply a PRA. I'm supposed to mention risk-informed. They do both. They do the classical engineering analysis they always did, and they do PRA. You have to do PRA. But they don't have criteria that were mentioned this morning for Europe. They don't have hard numerical goals that you have to show you meet. They have numerical goals that you should address, but they are not licensing requirements. NASA, interestingly, uses thresholds for judging the suitability of systems for human spaceflight. That's a little different philosophy. At the NRC, at the bottom of the slide, I'll just point out the Geologic Repository people don't call it PRA, but they did a very thorough analysis of performance with a lot of attention to epistemic uncertainty. And then, of course, I mentioned already hazard analysis-based methods and regulation of byproduct material systems. So there's a whole spectrum in a sort of graded approach in use at the NRC. Department of Energy has been very slow to require PRA. I think most DOE facilities that have that have appreciable inventory of radioactive material have PRAs, but not as a result of a headquarters requirement. They just think it's a good idea. And this is a clip from a fairly recent policy that's as warm towards PRA as I've seen the Department of Energy be. And you can see in the middle of the slide the quotes are why you would do one and how you would use it, relating to the same decision analysis text things I had on an early slide. Now, simulation-based risk analysis was the thing in the far upper right of the table I showed earlier. A colleague of mine put together a benchmark study to try to show what's wrong with fault-free event tree modeling. And this, I don't know how much detail we'll be able to go into here, but they contrived a problem with, this was for a 10-year space mission, and of course it's way out there, you can't fix anything, so they were carrying a lot of spares, and that's all the little units shown in the lower left are different propulsion units, and the timeline above all those units is when you have to switch them on and off as a function of where you are in the mission. So that sounds simple, and notionally it is, but if you begin to do it in fault tree space, it's just worse than daunting. It's just almost impossible to make sense of it in a logic modeling way. But it's easy, intuitively, to understand how the thing's supposed to work. When one breaks, you switch on the next. So the lesson drawn from this, well, he got 7 or 8 conference papers from people participating in the study. Every one of them that made any sense at all did simulation of some kind. So the conclusion from that was, you can see there, timing issues were critical in sort of defeating the logic modeling. And I believe I heard this morning mentioned at least once the dynamics, the changing situations that you face in regulating vast interconnected systems. It's really almost more like the grid. It's much more like the grid. Your problem is much more like the grid to me than it is like a nuclear power plant. Real world versus models. There's a fun Yogi Berra quote. In theory, there's no difference between theory and practice. In practice, there is. So at NASA, we invested a fair amount in precursor analysis. NRC has done it all along, well, all along since '79. And Mr. Hart mentioned the NASA event where foam had hit the wing leading edge. Well, they had precursors. After the Challenger accident, there was a lot of discussion of normalization of deviance. NRC did know, well, they knew that damaging the leading edge would ruin the spacecraft. But in the event, in the Columbia event, they sort of talked themselves out of believing that it had been damaged. But the whole saga of deciding what anomaly to focus on, that really is a hard problem. And that was the focus of our NASA precursor work. I think I have a reference to that later. Deciding when you need to take steps to reconcile your system with your model. That's a hard problem. Still, of course, we're still learning from that. So there's a point I need to get to here in the middle of the summary having to do with data. I would say that in our communities, in which I would include NRC, NASA, and the Department of Energy, a lot of us agree that there's a need to focus on scenario-based methods. And in that, I would include actually the hazard analysis methods that I had in the middle of my earlier slide. You don't have to be a full fault tree thing to be scenario-based. You just should be more detailed than having an engineering code telling you what margin you should put in. You need to match the analysis rigor to the decision being made, and you need to think carefully about how you're going to promulgate requirements. Data. There's been actually, to my ear, some divergent positions taken with respect to data. Some people would say, well, they're uncertain, but I would argue that the right way to view a risk analysis is to say, suppose my scenario model is complete. The thing about the data, if I like the answer that it's giving me, then I need to commit to achieving the inputs. The inputs are investment decisions. They're numbers you have to make come true. And that's a slightly different answer than just saying they're uncertain. Sure, garbage in, garbage out, but if you like the answer, you want to make that answer come true, there are engineering implications of achieving those reliability numbers, achieving that margin. So, not incidentally, by the way, and actually there was a slide like that this morning. If you have numbers in a PRA, in a owner-operator's PRA, a performance-based thing to do is ask whether those numbers are coming true, the inputs, not just the output. And of course, there's a whole body of assumptions. I mentioned in the case of the NRC models, they will shut down if you know you're in a bad configuration. You may not have that luxury, but that's just the tip of an iceberg of a lot of assumptions having to do with the premise that the facility satisfies basic engineering requirements. So you don't get to forget about those if you're going to believe your PRA. You have to understand what drove the PRA structure, probability assignments that you made. So in final summary, we've been doing this since the 70s, and we've learned a lot about doing it. The simulation-based stuff, if we combine phenomenology and reliability, that's extremely demanding, but as computers get better, it's becoming feasible. And we're learning better how to make more use of that. So that's the learning future for us in this PRA game. Thank you.
Thank you so much, Bob, for an excellent presentation. We're going to have questions at the end of this panel. Working. Our next speaker is Pranab Samanta from the Department of Nuclear Science and Technology at Brookhaven National Laboratory.
Good afternoon. I am Pranab Samanta from Brookhaven National Laboratory. Today I will share with you one particular work that we did for U.S. Nuclear Regulatory Commission that is related to developing tools for the inspection of commercial nuclear power plants. And these tools were developed in using risk informations and to conduct risk-informed inspections of nuclear power plants. I thought I'd give a little bit of introduction to the the nuclear power plants and inspection requirements. And so I have these brief 2 slides that would also give a little background for the specific things that I'm going to talk about. Bob has touched on many aspects of the USNRC's work. I guess many of you are aware of it, and probably many of you, as I realize, were involved in the nuclear industry. NRC basically is responsible for the regulation of the nuclear power plant to ensure public health and safety. There are about 99 nuclear power plants currently in operation. And as Bob was mentioned in previous discussions, that NRC has been involved in and developed probabilistic risk assessment tools for many of its regulatory activities, and they are increasingly used currently. And we have, as part of that, now because of NRC requirements, all the operating nuclear power plants have a plant-specific probabilistic risk assessment models done for them. And increasingly over the years, they have identified many uses, and they are increasingly being used. And these tools has been based on many PRAs that NRC conducted over the years, and NRC had developed extensive programs relating to risk analysis methods, data collections, and tried to use risk insights. As part of that, NRC defined safety goals. Those are goals, not a regulatory requirement, and also had policy statements encouraging use of probabilistic risk assessment and these tools. The specific, the work that I'm going to discuss relating to inspection of nuclear power plants are part of the overall NRC's oversight process. And I believe it's approximately 15 years back or so, with the availability of risk information, NRC was involved in the process of improving their inspection process using a new reactor oversight process. And it is during that process more risk information was used and was increasingly found useful to improve their overall process. The basic idea in the reactor oversight process, which is currently used, is to focus the inspections, and this will look very common sense natural, is to focus the inspection on activities where the potential of risk are greater. And in general, previously inspections had very large number of activities to conduct in a nuclear power plant, so the idea was to get them focused in activities those are of greater risk. In that way, you will get the maximum benefit of the inspection that are being carried out. And if you identify the plants those who are not performing well, obviously you would like to pay greater attention to those areas, and you would keep some normal level of inspection activities if the plant is performing well, so that in case there is a degradation in the performance, that you could pay more attention to them. And what was needed also, because design differences and the difference of performances, there were concerns that NRC's regulatory actions in response to the inspection findings were not necessarily very consistent, and there are variations among those, because as you can expect it, between inspectors, different types of inspectors, there is an opportunity to have different impacts or different actions in terms of their findings. And overall, so what was being sought after is to look at a consistent approach that where the actions are predictable, where the licensees would have a clear understanding of the manner in which the inspection is being carried out and the inspection findings are being implemented. And overall, as part of the process, the public also has an important role, and the whole process should be clear and transparent to the public. So with these goals, the idea was to develop an overall process, and the risk information and risk modeling were found to be very useful in that process. This slide gives an overall schematic of the process, and in a very top level, as you see, the top goal is the NRC's primary responsibility, which is to assure public health and safety. At the next level, you define the three strategic performance areas, the areas that you are trying to assure through your regulatory role. Those are the reactor safety, radiation safety, and safeguards. And then those different strategic areas are divided into what are called the cornerstones. And then we have the various cornerstones defined and below, the initiating events, mitigating systems, and barrier integrity, and so on. The models I will show will focus mostly on the reactor safety area. Those are the cornerstone on the left-hand sides. And then below that, there are three areas defined, which are called the cross-cutting areas: the human performance, safety-conscious work environment, and the problem identification and resolution. Those apply all the different cornerstones. So idea or the thinking in this and the slide is that if you're able to address all the different cornerstone and the cross-cutting area adequately through inspection, you probably would have adequately performed inspections and made identification of the issues that need to be addressed. So the oversight process and models try to systematically address all these different areas and, in a sense, try to maintain a similar structure and approach in the process. Now, in trying to apply the risk assessment tools in the inspections, what was one looking for was to somehow relate to the inspection findings to the risk implications. If that's, in a sense, gives a common currency, if you have a method that can be used across all the plants and can convert it into some risk number based on the findings. And in that way, there's some consistency can be achieved and some different actions can be defined. So what we were looking for is to get a methodology to do that. And what we tried to achieve here is to look for an order of magnitude determination. Now, this is important because by selecting an order of magnitude evaluation, we were not looking for that level of precision in our modeling, and that simplifies a lot of things. In that way, your burden of accuracy in the data becomes a little less. You can make some assumptions in there. And the reason we sought for order of magnitude evaluation, because ultimately inspection findings probably won't be made based on whether it made a difference in 5.10 to the minus 6 to 5.5 10 to the minus 6. You'll make levels of decision whether there's an order of magnitude difference relating to the finding that has been made. And so in that way, there was a number of simplification can be made. At the same time, your results would be adequate for the inspection decisions that you need to make. And similar to as we have seen this morning, we could assign this order of magnitude in different color-coded finding, red, yellow, white, and green. And when the impact was of the order of 10 to the power minus 7, that was green. And as I saw some slides in the morning, similar level discussion in your industry, and corresponding the red would be an impact of the order of 10 to the power minus 4. Now, this overall process of relating inspection finding is termed a significance determination process, whether when inspection finding is made on a particular facility and inspectors will go through evaluation of the significance of that finding, and that's why it's termed the significance determination process. And I guess in your industry, all other industry inspectors need to try to conduct similar kind of evaluation, sometimes qualitatively, but here is a process of a more systematic evaluation through the development of models. The overall significance determination process, again, is a phased process, as I mentioned in the earlier slides, that we are trying to focus more attentions on those aspects where the risk significance is greater. So initially, there is a screening. Inspector can screen those findings based on certain qualitative criteria, whether the finding is at all significant or not. And if he finds very early stage, relatively minor, he will screen out of the system. And then at the next level, you do an approximate analysis, and finally, in some issues, some findings could be a lot more significant than they may require detailed evaluation, detailed modeling in such cases. Typically, what we were trying to achieve in this modeling so that we can address 90% of the inspection finding to the second stage, so that only 10% or even less cases, they would need to go to a detailed modeling. And that, in that way, a large fraction of the evaluation inspector could be addressed quickly and can be resolved. Now, what we faced in doing this work, even though the nuclear industry had been working on probabilistic risk assessment models, and there were plant-specific PRAs available in all cases, but within the detail, there were a large number of variations in the model. And many cases, even in most cases, they used some form of event-free faulty modeling, but there were differences in those models, in the level they addressed, how they treated very specific issues. And so what we needed to develop are some consistent assumptions, because by treating similar issues consistently all across the models, we're able to, then only we could get consistent results relating to any defect, any findings that we found in a particular facility. And one of the other requirements, what we had was that since the inspectors should be using these models, and all inspectors may not be very familiar with the risk methodology, and the risk methodology uses a lot of jargons and a lot of terms that are familiar to that industry, but not necessarily familiar to the inspectors at the facility. So even though we were using risk information, we tried to present the models and present in engineering terminology that is commonly understood by the inspectors. These are based on discussions we had with the inspectors at the time we developed these models. So in that way, that the inspectors should be more interested in using these tools, and their training requirement on every button would be a lot less. As I mentioned, we wanted to give a tool to the inspectors that they can make an evaluation. They can make an evaluation themselves quickly in many cases. If they're able to make those evaluations quickly, then they could solve the problem quickly and resolve the cases and move on to other serious cases. So idea was to present a tool that inspectors will use quickly, and also so that they can use the tool. In a sense, it will have a feedback on the tool, so that you use these tools to select the features that they may be interested in inspecting, so that they can, from those models, they can figure out which parts of the plant have more risk impacts and which be part of their inspection, so that in that sense, inspection would get focused on risk-informed aspects, and also any finding they make then can be evaluated. They can make judgment of what actions they may need to take. This is an inventory, just to give you a feeling. Typically, the inventory models are developed in a nuclear probabilistic risk assessment. This is a simple example, and it starts on the left-hand side, what we call the initiating event, similar to your threat identification. And on the top are the different mitigating features. Some are systems, which are automatically actuated. Some are actions by the operators. So basically, we draw these trees to how the event would progress from the left-hand side all the way to the right-hand side. So either it has a successful terminations, which are okay, or it results in an undesirable event, which is a core damage. And so basically, we are trying to protect the undesirable scenarios. And so we have, this is one example, we have you have a 9 threat assessment, we have many initiating events in any nuclear facility. So all those events are analyzed, and as I said, we make, we developed this model for all the nuclear power plants, and we had to make consistent assumptions, develop similar threat identification, similar initiating events for each of the plant, and corresponding mitigating measures that are applicable. So we are trying to prevent any undesirable event when the upper branch of the road gives success and the lower branch are the failures, but this gives you a clear indications how an initiating event or a threat can become an undesirable event. So inspector's role is trying to assess that all the mitigating measures are properly would work, so that it can have a successful termination. And this is a little difficult slide to read, but this is the kind of this is the part of the tool and the kind of worksheet that we provide to the inspector. So there's a lot of information there. What we have on the left side of the column are the different mitigating feature safety functions that would come into play in response to a particular threat. And then there is a description on the right-hand side, and which gives you information on your mitigating features in your barriers. So the inspectors have clear idea of what kind of things this particular facility has, and next to it, it has certain nomenclature like a multi-train system, operator action, so on. So in their language, they are able to be able to convert that into assessing some risk impacts. In the bottom left-hand side, you see certain combination of events. Those are the combinations which lead to undesirable event, and you try to measure how the likelihood of those combinations has changed. So by using this worksheet, and you see simple numbers below there, and these are the numbers are given when everything is running normally, that is the likelihood of risk. And if a particular inspection finding is made, then by use that finding, inspector can assess what are the change in the numbers. For example, the multi-train system has a value of 3. If he finds that the one train of the system is defective, is not working well, inspector makes the finding. That means actually you do not have a multi-train system, you have a single train system. So the number will change from 3 to 1 or 2, depending upon the finding they have made. So by changing that number from 3 to 1 or 2, the overall number will change from number 7 to number 5. So this is a relatively simple that inspector could apply. So the risk impact have changed from 10 to the power minus 7 to 10 to the power minus 5, which is now somewhat significant, and he should address. In certain scenario may be low, and number will change, but it will still would not make difference. So the idea is behind it is a significant risk modeling effort is involved, but ultimately presented to the inspector in terms of the essential barriers that is needed in particular scenario, and the information is presented in a form that he can directly use and use for his inspection decisions. Of course, he's not handling only one worksheet. He has to handle a number of such scenarios, and these are computerized. He can use that, and the current information or the risk modeling information is available and presented in a compact form to him this way. And similarly, from these numbers, from this scenario, he can also choose the focus of his inspections. And he can use the numbers, the overall risk of the facility or response to a particular kind of threat, the various way it could be used. In terms of actions to be taken by the regulatory agency, obviously, there is a performance-based feature of the oversight process. If the findings of increased significance, higher levels of actions would be required. In case of the NRC's action matrix concept, depending upon the risk significance of the finding, if a very relatively minor finding, it is left to the licensee, left to the operators to take actions. And at certain level, if you are degrading a cornerstone, higher level management would be involved, certain other actions would be required. And some level, obviously, if you find major finding, if a risk to be very high, it would be as unacceptable performance, and the plant would be shut down. But what I was presenting is the tools that I was just showing as it is developed for all the facilities. So in that way, you can bring some consistency of the actions all through the plants, because all the inspectors would be used similar kind of tool, and they are all developed in a similar assumptions and in a similar manner to provide a guidance and the tools for inspector to carry out their essential activities. Yes, I will. Sorry. Okay, so as part of this, so there are a number of areas you develop the tools. There are safety cornerstone, different inspectable areas are defined as it narrowed, focused down various areas. Their guidance need to be developed for inspectors to carry on. Guidance need to be developed for using these significance tools, and the guidance for different aspects of the reactor oversight process as it addresses to the many features. So to wrap up, essentially, I have presented you a particular area. At the nuclear industries, the many areas worked on the risk analysis. I believe some of these features, some of the insights that we obtained could very well apply. And in this particular case, I think developing inspection guidance and tools should be very useful, and some of the insights that we obtained from this work probably would be applicable, hopefully would be applicable for your industry. Thank you very much.
Okay, great. Thank you so much. Our third and last speaker of this panel is Natasha Balak of the San Diego Supercomputer Center at the University of California at San Diego.
Thank you. I talk fast. I'll try and make up the time. Hi, thank you. So I will talk a lot about big data, predictive analytics, and how they can all be applied, and how could that possibly benefit building better risk models. So my background is in machine learning and artificial intelligence. I don't claim to be a pipeline expert, although I have worked in utilities for the last couple of years, and I'll talk a little bit more about that. So why are we talking about big data? There's a lot of hype about it. There's a lot of articles and conversations. The idea is that we have a lot of data coming from computers, from mobile devices, from sensors, from social media data, and we feel like we need to do something about it. How big is big data? People ask me that all the time, actually. And turns out that 92% of the data, of all the data that existed, was created in the last 2 years. Turns out about 82 to 85%, depending who you ask of, that is unstructured data. So these are all the big motivators for all the hype and conversations about data. There's a lot of estimates of how fast our data is growing. So one of the estimates says that a New York Times article that by 2020, we're going to have about 40 trillion gigabytes. Or now some people are talking about zettabytes as well. So I always like to say there is no good definition of big data. And I can't say that anymore, because now big data has actually made it into the Webster Dictionary. Now, this is not a great definition, and actually NIST is working on, they have a big data working group, which I've participated on for a couple of years. They're trying to define the big data and the reference architecture of the big data without really ever mentioning Hadoop or MapReduce and things like that, which is a difficult task to do. However, if you're interested, it's publicly available. So really the idea is that data is challenging the existing traditional, whether those are database management tool or computational tools, and that's what makes this challenge complex and difficult. As I said, not the greatest definition. So we have mentioned that data is coming from everywhere, and as you can see here, data is coming anywhere from structured data, from GPS location data, from machine data, computer to computer, a lot of text data. New cars produce up to a terabyte of data a day, transmitting back to the car manufacturers. There's RFID data, there's smart meter data, and if you're wondering what a terabyte and zettabytes are, you can see right there. People say 1,000 times, but if you're going to be really precise, it's 1,024 times bigger. So a lot of data. Again, what happens in 60 seconds on the internet? This slide is actually about a year old, so these numbers are even larger. But just take a moment and look at why is there such a hype about big data. This is just what happens on the internet in 1 minute. A lot of interesting things, right? So a lot of companies are looking at this and saying, how can we capitalize on this data? How can we use this to increase our ROI? So the idea is that behind all of this big data, that this is just the tip of the iceberg and that we can find more information. There's this hidden inside the promise of, large ROIs and things like that. I said there is no good definition, and honestly, the best definition, I believe, not that I'm here advertising any companies really, but IBM actually and Gartner both came out with kind of a descriptive definition of big data, and they said, really, it's the 4 V's that describe the big data. Now, if you go search 4 V's, there's 5 V's and 6 V's. Apparently, as the data grows, the number of V's grows. However, these 4 really describe the problem really well. So we've always had a lot of data that's challenging the boundaries of our IT system and challenging our databases and warehouses and things like that. But now, so that's an old challenge, maybe. You would say we always had that problem, right? But now we have a lot of data in motion. There's streaming data, thousands and millions and hundreds of millions of sensors everywhere. And data is coming to us as it's a firehouse of data coming us very fast, and we're expected to make some reasonably good decision, real time or near real time at this really fast pace. It's a difficult problem to do. Data comes in many forms. I said about 82 to 85% of data is unstructured. You have all those tweets and videos and a lot of text data that's out there that's not nicely in a third normal form in your database, so it's difficult to deal with. And the more data we have, the more uncertainty, the latency, ambiguities, the more data we have, the dirtier the data is. And in the machine learning community, we say that we spend 60 to 80% of our modeling time in data preparation and cleaning for these same reasons. So I actually think this is a better definition of big data because it really defines all the problems we're trying to deal with. Now, big data kind of quickly takes us into this thing called Internet of Things. Anybody has heard of that? There's a lot of write-ups about this lately, but the idea of Internet of Things is that we're now not only have connected computers, but we have connected things, devices, and there is this bidirectional communication, and now if we can put some intelligence, quote unquote, into those, now we suddenly have smart everything, right? We have smart cars, smart meters, every device can become smart because we're enabling this communication. But the idea is now that this bidirectional communication enables us to collect that data, use that data to create some interesting predictive models, hopefully, to be able to go back in that other direction and do some intelligent control over all of these devices, whether those are cars or houses or anything else. Guess what? That's taking us to a point where we're almost about to break our decimal system. Data coming from all of these networking devices is now growing even more rapidly and even larger. So now we're talking about brontobytes. Which is quite large. And so this is why we have a hype about big data. Now, that's all great. We have a lot of data, but what do we want to do with it, and how are we going to harness all of this data and find those insights and hidden information. This is where now predictive analytics comes in, and there is another, hype and a lot of conversation about it. Over the years, these terms have changed, and it started at something called, well, if you're talking about academia, it was machine learning, artificial intelligence. If you're talking about the industry, it first started being called data mining, which I actually think big data is a terrible term because you saw all the V's. It's not just the size. Data mining is just as bad because you're not mining for data. You already have the data. You're mining for insight and knowledge. If you're digging for gold, you don't call it dust mining, right? You call it gold mining. So anyways, minor differences. Then it turned into predictive analytics, and there was a lot of BI tools integrated with these predictive models. And now it seems to be turning into something called data science, and I'll touch upon that in a minute. But the idea is that we take these models that we can, bring and leverage from machine learning and artificial intelligence areas, and we can apply those to these large data sets. And we can try and model some uncertainty. We can use probabilistic models. We can use a lot of different things that can find these nonlinear relationships between our data. Sometimes you hear them called non-parametric models if you're coming from a more statistical. There is artificial neural networks, supervector machine, classification, clustering, hundreds of different models that have been now applied to these, to these areas. So, but the idea behind all of this is that we're going from a ton of the different data, whether that's sensor data, inspection data, third-party data, and we're trying to find some correlations in our data. When people ask me at a dinner party what I do, I say predictive analytics, and they're like, So I always like to give this example of when analysts went and looked at the grocery store in Midwest, they found when men went shopping for diapers, they bought beer on Thursdays and Saturdays. Those are patterns you probably wouldn't expect, right? So this is kinds of things what we're doing. We're trying to find these interesting patterns, these nuggets of gold, the needle in a haystack, whatever you call it, by using these models. They're based on a lot of probabilistic statistical methods, some of the AI assumptions that we make, and then there's a lot of recursion and a lot of things happen in the background. The idea is that we're trying to find these insights that we can actually take some actions upon that. It's been used in a lot of different areas, anywhere from marketing to sales to fraud detection to call centers and so on. So we utilize a lot of different models when we talk about this kind of large area of predictive analytics. And as I said, recently this has turned into something called data science, and there is now a new emerging discipline called data science. And I give a lot of talks about that too. So people ask me, who are these, mysterious data scientists? No one can find them. Amazon and Google are dying to find them and hire them. They're getting very highly paid jobs. What if I had experts in-house, what should I train them and how can they become data scientists? So if you think about kinds of techniques we use just to kind of bring these techniques to mind is machine learning tools, classification, prediction, time series analysis, multivariate analysis. We use a lot of graph analytics, maybe some visualization. But it's really the idea is that we always had geeks like me in the middle there doing all of these kinds of machine learning things. The idea is that now that's not enough anymore. There cannot be a person stuck in the back corner of your cubicles. That has to be integrated with the business. You need to ask the right question. You need to have the business analytics in mind as you're being inquisitive and looking at the right data to answering the right and have the right domain knowledge to be able to communicate via other departments across your organization and so on. Great example, anybody has heard of $1 million Netflix prize? This was years ago. Netflix, anybody uses Netflix? Okay, so everybody has been exposed to data mining, by the way. Now I've got to burn on this question one. Has anybody ever not bought anything on Amazon? Now, the other guy actually admitted that his wife buys stuff on Amazon. See, okay, so, all right.
You asked the wrong question. I paid for stuff on Amazon.
There we go. And so you have been exposed to data mining while they offer you products that other people have bought or similar products. That is all something called collaborative filtering or market basket analysis, all based on machine learning tools. Anybody has never received any junk mail? Again, you can thank predictive analytics for that too. However, Netflix had a great idea. Why don't we offer our data to the public and have people compete? And whoever can increase our predictive models to tell us which next movie is Natasha more likely to rent based on her previous movies she has rented and other movies that people similar to Natasha have rented. If you can increase that prediction by 10%, you get $1 million. It turns out that one team did at the very last minute 10.08% improvement in the model by using actually an ensemble model of collaborative filtering. And this kind of raised the popularity of a lot of these competitions and data sets and showed the promise of the increased ROI with machine learning. I just want to show you one quick example of what I mean when we talk about machine learning. Classification is a simple way of classifying or predicting new values. And what we talk in machine learning is that we usually have a set of attributes, maybe a pipe, size of the pipe, type of a pipe, year the pipe was maybe manufactured. And we take historical information about the data similar to that to the attributes that we're trying to learn. If we're talking about classification, we're trying to predict one specific class variable. For example, let's say we're trying to predict fraud in tax, and we have a whole bunch of information like that about the whether a particular person has received a refund, whether they were married, what their taxable income is, and we have historical information about whether each one of these people have cheated or not. We can take this information into one of the many classification learning algorithms. We can create a model, and that is the new data comes in. This is what we call scoring in machine learning. We can have the information about their marital status and taxable income, and we can make predictions, whether those are probabilistic or deterministic, whether we think this person will cheat or not. Now, these models are taking these multivariate interactions. They might find that if the taxable income was between 100 and 125K and it was a single female, then they never cheated. So it's this multivariate interactions of a bunch of these different variables that can separate this input space into sub-areas that can make better predictions. So how does that influence risk? Well, when we're thinking about predicting risk and risk modeling, we are often asking ourselves questions, if I have several risks at once, are they additive? Can we integrate quantitative and qualitative methods to make better predictions? Can we use historical data from the maybe failures or leaks or incident analysis to predict the future behaviors, maybe even down to the segments of the pipes? And so if we look at other industries, and some of those were already presented here, and I'm not going to get into the details, but finance industry uses risk modeling, predictive analytics to monitor and predict the risk of fraud on credit cards. Every time you get a new credit card, they call you, did you make these purchases? Yes, I did. If you go out of town like I do and they stop your card, this is because you're not fitting the model they have created for you. They create actually individual model to each one of us and then aggregate them to the more hierarchical set of models. Fraudulent claims, the insurance industry has used these techniques for many years. Marketing has been up and coming. They're probably the biggest adopters of these industries. They have something called uplift modeling, and they calculate churn. Every one of our cell phone service companies do that. They want to see who is the sleeping dog, who do you not want to touch because they might jump ship to the people who, if I give you this offer, you will take it, versus I'm sending you junk mail because you're not one of those people that might take this kind of offer. All the way to Airbnb. Anybody knows what Airbnb is? They actually calculate the risk of customers who are not necessarily welcome at other people's houses, renting them. So we have done some, and they do it real time. They're actually quite good about it. I've done some work in utilities and on my UCSD research job, as well as we've done some things in our consulting. There's a company in San Diego that we have been collaborating with. To just give you an example, they have a very sophisticated model, transportation company. They install video cameras into all the trucks and buses that transport people or goods. They collect the data about the weather, the roads, GPS, acceleration, information about the vehicle, as well as the driver, to very accurately predict whether this driver is about to have an accident or not. They're so good at it that they're now packaging this and selling it to other companies, and they were really, really good in decreasing the number of accidents, using very complex hierarchical machine learning model to do that. We've done some work in utilities. I said UCSD has one of the most advanced microgrids or smart grids. We make 92% of our own energy, and we have PMUs, or phasor measurement units, which are sub-second sensors that actually tell you about the stability of your system. And we use some FFTs to find frequency correlation. And you can tell, we use several different methods, that we can totally tell between the event and the normal operation, right? And that's really great, but if I'm telling you right now there's an outage, not that useful. So what we have started doing is applying some of the more non-parametric methods, including k-means and PCA, principal component analysis, and support vector machine, to take information that we're getting from the PMUs and be able to increase that window of warning before the event actually happens. And that really directly applies to a lot of things pipeline industry does, is you don't want to say, oh, well, we have a large event right now. You want to see, as you're going to that event, how are your variables changing? What is the probability of that event actually happening? So if you take that specific example and you have the whole idea of the big data and all the data you can possibly collect about your assets, and you're looking into sensor network databases, expert information, inspection data, different assessment methods. As I said, we spend a lot of time cleaning and prepping the data, so you hear a lot about feature selection, feature engineering, reducing the number of features, looking at the uncertainty of your data. Then you can take all of that, combine the statistical and the information that's coming from the experts, and run them through a number of these predictive analytics to look at using probabilistic predictive risk modeling scores. And as I said, the ensemble approach and multiple risk modeling can be combined into a unified or a risk number that comes out. These are the pictures, and someone earlier mentioned the Bayesian networks and artificial neural networks, many different methods that can be applied to this. So I've mentioned feature engineering, and in the whole area of machine learning, and a lot of startup companies, they're using these algorithms to achieve all kinds of different things, anywhere from retail and marketing to predicting human behavior. We can looking at relationships at the parameters and these nonlinear relationships to increase the predictive power of your risk scores. And for example, we might want to look at the weather and the ground movement, but which aspects of those are really important? This is where machine learning can come in play. We can do ranking of the attributes or look at attribute important analysis. And some of these methods will actually exclude the attributes that were not important in predicting that particular outcome. So my message, keep calm and analyze big data, but really, use that data wisely, because big data can overwhelm your methods, and you do have to understand what you're doing with that and ask the right questions. So if there are any questions, I'd be happy to answer them. I think we're running out of time, but I'll be around today and tomorrow, so I'm happy to chat with anybody. Thank you.
Yes, thank you. We welcome your questions. Please state your name and organization if you have a question for our panel.
I'm Scott Randall from GBMC in Houston. I found it very interesting, Bob's comment about looking at, if you like the way the model behaves, if you like the way it's working, instead of focusing on the uncertainty in the inputs, let's look at how we can make the inputs certain in order that the model will work the way it does. And then tying that together with the whole assessment of barriers that was a common theme with Pranab's also discussion, and bringing that then together with the predictive nature of big data, and then layering on another. I guess I'd like to ask, how can we layer on another level, which is this whole field of human factors and behavior, loss causation models, and human factors? How can we look at barriers, not just mechanical barriers, but operational barriers that involve necessarily human factors, and then layer in maybe some of the inspection the risk-informed inspection techniques that Pranab's talking about and take some of the data maybe that we have about populations and the workforce, and then factor those into some kind of a protocol. Have we seen anything like that around layering human factors, barriers, and this data issue? Maybe you could address that, all three of you, because it seems to be something that kind of ties the three of you together.
Go ahead.
I'll start. Well, a risk analysis that doesn't look at the human element is just lacks credibility, really. That's been appreciated for decades, I would say, at least in the nuclear arena, and then every accident report goes back to organizational factors. I think we have trouble really modeling organizational factors in a fault tree, and yet organizational learning discussions do crop up in discussions of precursor analysis. So, in fact, I've seen a paper arguing, well, multiple papers arguing that if you're going to do precursor analysis, it has to be in an organization that's not a line organization. If you have a problem in the field and you're a field person, you're going to fix the problem and move on. So thinking and learning, those activities have to be considered and undertaken systematically, not necessarily by field people. But to go to the other, to me, the business about collecting information about what people actually do, we could do a lot more of that than we do. Over to you.
Well, I would like to echo that, and for years, there was a belief that you couldn't model human behaviors because they're so unpredictable. Turns out you can model a lot of human behavior. It's never going to be. None of the models we ever make are 100% correct. So, keeping that in mind. As I said, lytics models, when a driver is more likely to have an accident based on the kinds of behaviors that are leading to behavior of an accident. We use predictive models to model what you're going to buy next. So if you have enough historical data and examples, you can certainly make more predictive models. We have an ongoing project right now, actually, with a very large solar farm that's right kind of in front of Vegas, if you've ever seen it. And we have noticed that depending on who the operator was, there were significant differences in the amount of solar energy collected. And it turns out that each operator has their preferences or how they're actually putting solar panels. So we now have all the information about the different settings, and we're looking at what are the patterns of those. Can we make better predictive models to maximize the output of solar energy? So if you ask me, as much as if you have a lot of good historical data, we can typically come up with pretty good predictive models, but it's back to that, good historical data is not easy to obtain. And so, which I think I would like to echo our previous speaker who said, if the community comes together, and I know there's not a lot of examples of very large, maybe leaks or ruptures or very large events, but if every company put their data together, then we have a larger set of historical data we can learn from more and make better models, so.
I'd like to mention that, as Bob said, the risk analysis models typically these days would consider human role, the human reliability analysis, so on. And the probabilistic risk analysis model that are done for the nuclear industry take explicit care to take the operator actions and so on. And in the models that you are developing for the inspectors, if you noted there are specific operator actions that are involved that are noted there, and inspectors takes that into account. Now, we are focused at that model, the specific actions that could directly affect the accident scenario, but the likelihood of that operator action can be affected by the organization or many other factors. And we don't necessarily always develop the model beyond that because that's where uncertainty level increases, but that's something could be attempted. But significantly, the important operator roles are, you definitely want to make sure that you model those, even if you cannot do. So even if you cannot have all the detailed model, but to identify the specific areas which are major contributor to the risk and try to address those, I think is a very, very important. For that, you don't necessarily need to have all the data, but at least make sure to assure that the important areas that you have addressed are adequately included and refine as you go along.
I have one small point. Sure. In the nuclear area, commercial nuclear plants are operations are heavily proceduralized. Accident response is heavily proceduralized. And the structure of those procedures, I think, drives our modeling. And so while I would stick with a generic claim that a risk model that neglects the human lacks credibility, but I think it has to be appreciated that different industries are going to have to do maybe different things than the nuclear industry did.
We may have time for one more question. If not, then we're going to take a break.
It's up to you.
Okay. Okay. We will.
Yeah, thanks.
We will take a 10-minute break and resume at 3:30. Thank you.